Welcome to Functions and Function Notation. What we were doing in the previous section, we were working on solving equations with a restriction on the solution set. Basically taking an Algebra 1 skill and putting a little bit more of an intense spin on the back end. That is the restriction of the solution set. So what we're going to do in this section is just talk about relations versus functions and try to eliminate any misconceptions that you've had, clarify any questions, and then again, putting a little bit more of a higher end spin on things. So go ahead, press pause now, and copy all of the information through the red writing. Don't worry about any of the stuff on the bottom of the screen. All right, make sure that you date your paper and put a title on the top. Press pause now. Okay, well the first thing we want to do is we want to discuss the difference of a relation versus a function. A relation is pretty simple. It's a set of ordered pairs. So I have 3 ordered pairs here. That would be our set of ordered pairs, and any set of ordered pairs counts as a relation. What makes a relation a function is the following. A function is a relation that pairs exactly one value from the input or the domain to exactly one value in the output or the range. So we take a look back at our relation. -2, that's one of our inputs, pairs with 0. 3 pairs with 4. 7 pairs with 23. So this fits our definition of a function. Now what I'd like to do is to just add another number to the set. Well, let's bring 5, 4 up here. Is this still a function? Well, as I cruise along, I see -2 goes to 0, 3 goes to 4, 7 goes to 23, and 5 goes to 4. I went through quickly, really, because I just want to get over to this 5. 5 gets mapped to 4, and a lot of students say, well, 3 got mapped to 4, so this isn't a function. That's not the definition. The definition says that only one value in the input can go to exactly one output, meaning if 5 shows up again, it should only go to 4. Let me see if this clarifies things. I'm going to take 5, 4 out of the picture, and I'm going to put 3, -2 up here. Now what do we see? If you take a look, we have 3 is in here 2 times. One element of the domain, 3, gets mapped to 4. It also gets mapped to -2. That's not part or not satisfying the definition. 3 cannot get mapped to 2 different places. It can only get mapped to exactly one value in the range. And even if we went ahead and added 5, 4 into the mix here, we're still not a function. Why are we not a function? Because of the 3, -2. If I took the 3, -2 out, put the 5, 4 in, we're back to being a function. Let's see if we could clarify this using a picture. If I had the set of numbers that I had there, we have the 3, 4 and the 5, 4. So what I'm going to do is I'm just going to map those out. 1, 2, 3, 1, 2, 3, 4. There's 3, 4. 5, 4 is 2 units to the right. And the test for this is the vertical line test. As we roll the vertical line through the picture, well, let's not roll on the line, we're okay. It only hits each point on the function at one at a time. If I added the 3, -2 into the mix, and I plotted that, 3, -2 is going to be right about there. And again, as I grab that vertical line and I start testing, boom, it hits both points and it fails our vertical line test. So what this means is when you send one value of x to 2 different places, you're going to end up with a picture that looks like this. Not exactly, but at least 2 points above or below each other. And that's not possible if we're talking about functions. This would simply just be a relation. Let's try some more. Now we're going to try to look at functions from a different perspective, an arithmetic perspective. When we look at this, we have function notation. And function notation is the way we prefer to write things in Algebra 2. F of x is simply a fancy way of saying y. The reason we prefer f of x is because y is a direct result of what x was. So for our first problem, I'm going to take a look at the value of x being -3. So I'm going to write f of -3 equals 3 times -3 plus 2. Okay. Continuing along, we're going to say that that's -9 plus 2, or -7. So f of -3 is equal to 7, or in Algebra 1 terms, y is equal to -7. But we really want to avoid writing it like this. We want to stay with this version, the adult version, or Algebra 2. That's what I call adult. What I'd like for you to do is to press pause, find the values of f of 0, f of 3, and then place all of those values into your table. I'll wait, you press pause. Okay, did you get the same y values that I got? Hopefully. -3 gets paired with -7, 0 gets paired with 2, and 3 goes with 11. So if we were to write those as ordered pairs, we'd say -3, -7, 0, 2, 3, 11. When we're looking at just the ordered pairs, we'd say, well, no x value shows up more than once, so apparently each x value only gets mapped to one unique spot. Well, what if we were to add 3 into the mix again? Well, if you substituted 3 back into your function, of course, it's going to have a y value associated with the same value it was the last time it was substituted in. That's the whole point of the function. An x value, when substituted into the function, couldn't possibly get mapped to a number different than it was the first time that it got substituted in. Now, if you just take a minute to draw a quick sketch, I know I cheated. That's what it looks like. And if we were to draw a vertical line and then pass that line through this picture, we're never going to hit this thing more than one time. Now, I know I have a little bit of a crooked line right there, but just for argument's sake, there's the function. And for the sake of time, I noticed that my writing had gotten cut off earlier when I was speaking. I said that I wanted to write this as f of -3 is equal to -7. In Algebra 1, you used to write it like this. As I said, this is the way we write it now. Okay, let's move on. We should have a better sense now as to what the difference is between a relation and a function, both if you looked at just a set of ordered pairs or if you looked at a picture. Now we just want to step it up a bit. So looking again at our function f of x equals 3x plus 2, I have the beginnings of a table over here. Again, on the left side of the table we have our x values, and on the right side we have our f of x, our function of x values. And I have sort of like the whole real number system considered here. Now you could go into your calculator and you could look at a table of values, an infinite list. And so what I want us to do is just think about, what about the value when x is -infinity? That is, what happens when this value is a huge negative number? First, we're going to triple it, and then we're going to add 2 to it. And so what's it going to be? It's still going to be a huge negative number. As we continue the process of substitution, we'll see that -3 goes to -7, that we already knew. -2 goes to -4, -1 goes to -1, 0 goes to 2, 1 goes to 5, 2 goes to 8, and 3 goes to 11. Now I said goes to, what I really should be saying is mapped to. So -3 gets mapped to -7 and so on. And as we continue on, what happens at the very bottom? 3 times a very huge number, again, is a triply huge. And the negative side, it was a triply huge negative number plus 2, which essentially just leaves it as a huge negative number. When you take a huge number and you triple it, on the positive end, you get a huge positive number. And when you add 2 to it, it doesn't really do much to change it. It's still just a really huge positive number. Now, what we want to do is consider both of these columns one at a time. First, let's consider all of the x values. All of the possible inputs that we could put into this function, we're going to refer to that as the domain. And all of the possible outputs, this list on the right side, we're going to refer to that as our range. So really, it'd be easier just to throw the words right above the columns that they were referred to. Now, I'm starting to refer to these, my x values I associate with my domain, and my f of x, my functions of x, or my y values, I associate with the range. The way I keep this in order, d comes before r, x comes before y values. Domain and range. All of this I consider to be prior knowledge. What we're going to do now is simply use our number set terminology, and you say, what if I were to restrict the domain? Yes, I want to restrict the domain, and I'm going to put the domain right over -1, because what I'm going to do is I'm going to say I'm only going to consider whole numbers. Well, what happens when I restrict the domain to all whole numbers? I'm only going to consider numbers from 0 on down to positive infinity. Well, what happens to the range? Well, you can see with the table of values that the range would be restricted from 2 on. And now we're going to express this in terms of interval notation. Okay. Interval notation doesn't have to be anything scary. It's just a nice tidy way of writing all of the values of the domain and range. So if we restrict our domain to all whole numbers, in interval notation, what we're going to say is that's from 0 all the way to positive infinity. Since 0 is included, we're going to put a whole bracket on that. And since infinity is more of a destination, not a value, we're going to put open brackets on the right side. The hard bracket here on the left means that 0 is included. Hard brackets are an indication that the value it's next to is included. Parentheses are what we refer to as open bracket, or a soft bracket, some people say, would indicate that the value next to it is not included. That being said, let's take a look at our range. What values do we start at? Well, if we look over at the table of values, we see we started at 2. So we're going to go from 2 all the way to positive infinity. Is 2 included? Yeah, 2 is an actual value. And is infinity included in our answer? No, it's a destination, or a theoretical destination, not an actual value. And so that's what our domain and range would look like. Or these two things help us express these are all of the possible x values that we would use to calculate all of the possible y values that could come out. Let's try a couple more. Let's take the function f of x equals 4x minus 3. And let's consider a domain that's restricted to natural numbers. What I'd like for you to do is to take a moment. Over in the x column, I want you to place the very first natural number that we're going to use. List 2 or 3 after that, ... and let me know where it goes to. After that, I would like for you to evaluate f of x for the values that you've given. Let's see how you do with that first. Press pause. All right, welcome back. How'd you do? Hopefully that was easy. Now what I'd like for you to do is I would like for you to express the domain in terms of interval notation and express the range in terms of interval notation, and see how you do with that. Press pause and try to use the correct brackets. Now, for this particular function, both the domain and the range are expressed in the exact same fashion. That's just a coincidence. It won't necessarily be the case. What we're going to have to do is we're going to have to think, yes, I said it, we're going to have to think about what happens when we change the x values. Are the y values going to get larger or smaller? Are there going to be some impossibilities? This is going to be the whole key to this sort of stepping it up to the next level. It's the thought process behind domain and range. All of the mechanicals that you're doing here is a skill that you've already possessed. On the next slide, what I'm going to do is I'm going to restrict the domain in a little bit more of a notational manner. Alright guys, for our last example, we have f of x is equal to negative 3/2 x minus 2. Now what we're going to do for restriction here is only consider the x values that are greater than or equal to negative 2 and less than or equal to 16. So for our domain, the way we would write it, other than in this fashion, is we could say that the domain is equal to negative 2 all the way, comma, to 16. And since we have equal to's on both of those inequalities, we are going to consider both negative 2 and 16 as part of the domain. It is closed on both ends. Take a minute now, press pause, and evaluate the f of x values for the given x values. So for negative 2, negative 1, 0, 15, and 16, you should have y values. All right, take a minute, press pause, do that now. Don't wait for me to do it, you got to do it yourself. Okay, now hopefully your values match up with mine. I have negative 2 maps to 1, negative 1 maps to negative 1/2, 0 maps to negative 2, 15 maps to negative 49/2, and 16 maps to negative 26. If we were to graph this quickly, we have negative 2 as our y-intercept, and essentially that's what the graph looks like. This is just a line coming down, a slope equal to negative 3/2. Now let's just shrink that down and park that over here. The last thing we want to do is just identify the range. So where does our range start? It starts at a low point of negative 26 and goes to a high point of 1. I know that we started at an x value of negative 2, but when we phrase the range, we want to phrase it from the smallest value to the largest value. So the smallest value that we have is negative 26, and that is included, and that goes all the way to positive 1. And that's all we have. We'll see you in class, and hopefully this wraps up any questions you have with functions versus relations, your notational skills, and domain and range notation and understanding.